Okay, so hello everyone. I'm delighted to be here to present my work with you. So today's topic is spray formation and spray workflow interactions within a GDI engine, a flow bench study. So I'm Paul from STV2 Darmstadt. I'm a PhD student. Let's get started. And okay. So before we directly jump into the topic, I just want to give you a motivations why this work is important. So if we look at the time evolutions of the development of internal combustion engine from the carbon red engine towards the GDI engine, where we can see this fuel consumptions actually drop up to threefold. And on the other hand, if we look at the specific power, it's actually boosts up to 3 times more. Then now, if we look at market share of the GDI engine from last year, we can see it's still climbing up to 30% of the overall total market share. And the GDI hybrid systems also climbing. So which means, there's still room for us to develop. However, I understand now we're still a headwind ahead, meaning that the zero carbon emissions. But we are still advance ourselves toward the e-fuel and hydrogen. Okay, so now this study, we only focusing on the Darmstadt engine flow bench. As you can see, the process of the internal combustion engine from the intake flow to the combustions. There are actually lots of sub-physics happening. Then this study, we only focusing on the spray formations and mixing during the early injection condition, which means that it's inject the fuel during the intake phase. And to reduce the complexity of the engine flow, I think the engine flow bench is a good candidate because it's operated with the fixed valves and the piston removed, which means it resembles a stationary operation. Then on the right-hand side, you can see a target experimental kit model as well as the numerical one. So now I want to introduce you the our modeling development roadmap. So we start from the small scale, which is in a nozzle flow DNS. Then we toured to the constant volume chamber. This is a free spray, what we have been done. And then we advance ourselves toward the spray wall impingement. And once the single geometry was well validated, we move to the complex geometry, which is engine flow bench. All right, so as you can see, the scale from the small to the large, and meanwhile, the resolution also reduced from DNS toward LES. Okay, so here is a numerical setup, what we are using and developed for this study. So we're using large eddy simulations, then OpenFOAM is V2012. So if we look at the DNS data here, so every time we are making a DNS data or we're making a DNS simulation, we always want to get the real physics or a correct physics out of it. And we will hope we could get the model from it and develop a physical model. So what is that? So this is the injector hole. And the blue one actually represents a liquid core. And the red one represents a total droplet. So meaning that, so each sections in between, they're only 0.2 millimeter, so which is really, really small scale. And if we look at P6 location, which is only 0.6 millimeters away from the injector tip, then the total liquid core is totally break up, become a droplet. And if we, to give you a more clear idea, so we printed out the P6, all the droplets on the breakup region map. So coordinate with Ohn-Sold number and the local gas web number, then you can see none of them is actually encountered the shear breakup, but rather the droplet oscillations and deformations. So this is actually a good information for us to develop our model suitable for the GDI engine. Then we applied the statistic droplet distribution model from the inner nozzle flow. The same, we developed a dynamic breakup to dynamically calculate the parameter of the KHRT. Then since the deformation of the droplet was happening, so you probably will have this prolate and sphere and oscillate. So we also consider it in a drag model. So this is how the whole suite of the Lagrangian Lagrangian model we're using for the spray. Okay, so now after introducing all our suite of Lagrangian model, we are going to validate if the model works well. So we cooperate with Sandia, and here is a ECN experimental data setup from the spray G. And to make a more consistent comparison, so we convert our Lagrangian particles toward the project liquid volume and facilitate a direct comparison of the plume shape with the experimental data, a DBI shadow, DBI imaging. So there are two conditions, which is G3 and G3 cold. They are chosen from Sandia, which represent as early injections. So what does that mean? It's like when the valve's opening and you inject, so you assume the ambient condition should be 1 bar. So here is the validation data. So let's have a look if we captured quite well. So the blue line is actually simulation data, and the black line is experimental data. Okay, so the really good agreement, I assume, has been reached. But by looking at the plume shape, you can see these two conditions actually not much differences. So to understand more, we extract the total liquid mass ratio, so normalized by the total injected mass. So you can see how much mass you have already evaporated. Then we can see a G3 case, given that it's only 70 degrees higher compared with the G3 cold case, it has like 50% more evaporation. So now the simple geometry, we have well validated in chamber. We go further to the complex geometry, which is engine flow bench. So now here is our mesh strategy, what we're using to capture the spray. And since the engine is a confined domain, which the intake flow and incident flow are actually influenced by the wall. So either there are two ways to solve the problem. One is to use the wall model LES, or you are using a wall resolved LES. And in this case, we certainly doesn't want to use any uncertainties from the wall modeling. So we are applying the 15 layers on the wall to facilitate the wall resolved LES. And on the right-hand side here, just give you a quantitative comparisons with the experimental data. So this is now DBI, it's misscattering. And since we have, we're using LES and we have ambient flow, is quite different from the combustion, from the constant volume chamber. Then the ambient flow is actually influence the spray formations. So therefore, we are calculating the 25 consecutive injections, and we make the phase average. Okay, so first of all, I'm just saying the black dashed line is experimental data, and then the blue solid line is a simulation data. We measure quite well, but when you can see, as we increase the mass flow rate, you can see the overall plume shapes got distorted. And here, the left-hand side part is stretching by increasing the mass flow rate, and right-hand side, the overall plume is actually swing to the right. So here, to give you a clear idea, I attach all the three conditions of different mass flow rate together, and you can clearly see how does that distorting. And also the same also happening in the experimental data. So now we are gonna investigate these phenomena. So how to do that? So this GDI injector actually has 8 holes, if you can look at here. So we give the index of each injector hole, and we extract the mass and the penetration length. Then we can see how was that happening. So we assumed if the injector is axisymmetric, then they should have homogeneous phenomena. However, this is actually a heterogeneous phenomenon, but we can still categorize somehow. So if we look at the plume on the right-hand side, which is far from the intake valves, so the plume actually have a more evaporation and more distortion by the intake flow. And on the right-hand side here, which is close to the intake valve, has less influence by the intake flow, then you will have less evaporation and you will have less penetration distortion. But the most interesting is the plume 5 and plume 1, which you can see here, the plume 5 and plume 1. So the plume 1 is the farthest one. I expect it should have the most evaporation, but however, there's less evaporation and the prolonged penetrations. On the other hand, the plume 5 close to a intake valve actually has more evaporations and the most distorted penetrations. Then what's that? So we extracted the liquid volume of the spray, and the vector here represents a velocity. So now you can see on the left-hand side here is the plume 5 actually penetrates, then it dissipates, and the structures got destroyed in the on the pathway. And the story happened quite different of the plume 1. So we give you a good idea what is going on there. We put in out the velocity field. Then you can see when the two intake valve, when two intake flow comes through from the two intake ports, they actually converge together, have a strong vortex in the middle, and this strong vortex actually just on the pathway of the plume 5. So therefore, when plume 5 penetrates through the vortex, they actually dissipate and destroy the structure. On the other hand, if we can see it here, it is we can see. If we can see there is a tumble flow, and then the tumble flow is actually give the momentum of the plume 1 and to prolong the plume 1. Okay, so now we are looking at the other plume, which is plume 4 and plume 8. So I assume if the injector is if the injector is axisymmetry, so the plume 4 and plume 8 should be similar as plume 6 and plume 2. So by looking at these two parts, you can see the plume 8, which is on the right-hand side. Wait for the animation. So it's actually also it got influenced by the intake flow. But something interesting is the plume 4. So the plume 4 here is actually hit the valve wall, and when it hit the valve wall, it can generate the wall film, and the wall film might create a soot, create a misfire. And this is the hesitate. This is a thing we certainly want things to happen. So we are using a single layer and then developed a suitable spray wall impingement model, spray wall interaction model to capture this and to see how, if we increase the mass flow rate, what's the convection evaporation effects can reduce the overall mass. Then we can see that as we increase the mass flow rate, then the overall fuel mass actually decreased up to 50%. Okay, so to the end, I'll just say our model actually captured quite good in the simple geometry, which is a spray chamber, as well as the complex geometry. But so far, everything is steady, so no moving mesh. Then we are going to move ourselves to the real engine applications, which my colleague Andrea Pati will present later on. Then we're going to move toward the multi-components view, E00 and E10. And I also have some preliminary results in a poster room, in poster session before. So if you are interested, you can have a look there. Then we are going to the methanol fuel to understand. Okay. And I put the the bikes. It's not just encourage you to run the bikes, because like took a metaphor from ECN. So given that we have headwind ahead, right? So we have achieved a lot in the past, then we can still achieve and overcome this headwind. So just cheer up the engine group. Thank you.
So any questions from the audience here?
In the spray itself, or yeah, I mean, this is just application. We are apply for the combustion engine, but the know-how is actually we can keep the know-how and apply to different. So you can have now we are transforming ourselves to the methanol. Then probably okay. The volatility probably different. Then but still the know-how is still there. So we can still apply. Given that this study is iso-octane, so we can apply just different fuels. Yeah. Or pharmaceutical. So I have another colleague actually doing the spray. We were working together. Then he got a job for the pharmaceutical company doing the spray as well. So I think it's kind of multi-applicable. Yeah, region. Thank you. Is that Lagrangian model? Yes. Yeah. So then you describe product size. Right. Right. Yes. Yeah. So we get the necessary data from DNS. This is how we want to run DNS because otherwise it's just too expensive. And yeah. It's actually a one-way coupling. Okay, so there's another way to do is you do the whole structure. So maybe I go this one. So there's other way. So you do this DNS simulation and then you restore all the necessary data from, let's say, P6, which is this part. Then you start to apply to the Lagrangian. Is what I'm saying, right? Yeah, but we have one solver doing directly transform to the Lagrangian field. But the problem is you're gonna solve the whole domain. Then this part is, let's say, micro, and this part is millimeter. So it's totally different scale. Then you would So I can tell you, like, here is 125, the minimum cell size, micro, and here is 1 micro. So it's 125 times more. Yeah. Then if you bind it together, then CFL number is always the smallest one, which is forever. Spreadsheet configuration. Yeah. So far, the GDI goes on the whole type. You're talking about the type of the injector. Yeah, that's great. You mean the operating conditions? Right. So flash boiling, I didn't show here because the flow bench study is based on the G3 case. Yeah, to be honest. But we have G1 case in the poster. So if you're interested, you can have a look. Yeah, sure. Good, of course. Okay, so welcome everybody. I'm here to present a couple of work, and as well, my colleague has introduced you. We are moving towards advanced fuel, which are CO2 neutral, and the point is that this CO2 fuel actually in engine are some critical part. So why we want to use this biofuel? Because they help us to follow the strict emission standard, and actually they help us for the European Green Deal to achieve zero CO2 emission. What's the problem of such ethanol and methanol, or in general all the oxygenated fuel? We need a lot of amount to be injected inside the engine. They potentially are corrosive for the metal parts of the engine. They are also prone to oil dilution, especially during cold start operation. And from cold start with the modern engine and hybrid solution, it's extremely important. What that means that what we expect in such engines is that we have a lot of warning engines. And so we have to understand all the phenomena in such engines. All of these, it's all the phenomena, actually. And
Here it's an advantage, it's a bit of advantage on OpenFOAM because thanks to OpenFOAM and there's open source flexibility, we can actually take a really different model and cover all the stuff together. Because you see that we have several problems. So we have multi-flow, turbulent, combustion, knock prediction. It's a lot of problems. But today we will just want to focus on the drop of the wall interaction and how we can solve it in engine simulation or in general in complex geometry systems. So we want to show and see if can we use this tool for deposit prediction for such configuration for real case. So this is the tool that is built on top of OpenFOAM. It's that we developed in our department. That it's actually covered all these utilities here. We are used to simulate all of this stuff. And actually, our work focused especially on that is the LES. We want to move to the LES because LES are really give us a little really detail. And for example, I see that with LES, we can go very and actually we can see that the different cycle, so we need an LES to provide such amount of data. What's the problem of LES? LES is a fantastic tool, work perfectly, but we need a specific mesh function tree. Why this? Because this is the point is that we need to have a such square. What does mean that in this case we need what is the keyword here? That engine moving patches with topological change altogether, and we have to find a way to integrate this in wall field simulation. And what is the point that we have to find a robust and cheap methodology for wall field to simulate such approaches. Okay, this is also layering. We see that here again we have a configuration of layering and radix deformation. Okay, here it's the key point of this type. This is the standard wall field methodology that is normally used in the electrician. This is the Muthaiah methodology. This is the sequence of the field. We don't compare all the day, so okay, it works. But sometimes can be difficult to use this approach on topological change and deforming mesh. That's always a problem. During the years, I worked a lot to and one day I wake up in the morning and said, okay, but why? So we know that Eulerian and Lagrangian description are just a description to the same type of problem. So a problem can be described both in Lagrangian or in the Eulerian methodology. Applying to Lagrangian, one you need to describe also the wall field as Lagrangian. And this is the approach on the right. Seems to be simple. So this was my idea. So let's see what happens. Okay, but the point that was when I wake up, it was simple. So I said, okay, we need something a bit more that can be compared to the already. And that was the idea. The idea is that, okay, we have our spring standard. No, we impact to the wall. Okay. Then we have our wall model. Okay. If we give mass of the parcel, that amount of mass, it must be transferred to a wall field. Okay. Let's remove that parcel from the Lagrangian spray and put it in another Lagrangian spray. This is the first trick. The second trick is the Lagrangian field. Let's transport some topological information. So which phase we hit, in which position we get the hit, and so on. And of course, velocity, Weber number. Then we get the reason. We get a buffer Lagrangian field. Then can we construct, for example, all the information between most of this information on the rest of the and so on. We can use this information to update the model. Then we obtain some source. And this distributes all the source to the function. So this is our cell. We have here a couple of parcels, which now is part of the wall field. We can distribute the salt cell to all of these parcels that are belonging to this cell. Not this one, for example. This one is out of that cell. This one will get another salt cell, and so on. The salt cell comes from the information of the Eulerian field here, which we reconstructed temporarily. Would have mentioned that with this approach, the topological change are automatically managed because it's necessary. Okay, we just have the position, we just have to update the cell information. That's it. Actually, working model will be the problem, we don't have a problem. And we will have let's simplify the management of the code, and it's also easier to parallelize. We don't need anymore to take care of it, to get in this, and so on. But algorithm. Why? This is especially important for complex configuration. Because in engine, but in general, there is a lot of complex configuration. We have our piston, I don't know if you see that move on the bottom. So these are fixed, and this is moving. Okay. But when we simulate in an engine, sorry, in TFT, this is moving. This is deforming. So this is also moving. But actually it's a fixed value. So a parcel that stick here must stick here, because in the real life, the wall is fixed. But in the TFT, that movement is moving as well. So we need two tracking. One tracking for parts that are fixed, but they are moving. Tracking for parts that are moving and they are moving, and tracking that for parts that are fixed and are fixed. If something is not clear, stop me during the explanation so we can discuss. I really want to, so it's really work in progress, this, so I would like to discuss with you. So this is the table of the AD. So the evaporation we can do both with Eulerian and Lagrangian. The momentum transport at the moment is only possible with the Eulerian field. Topological change are actually on the part of Lagrangian, but let's discuss in future some development of the Eulerian. Impingement regime, no problem. Impingement pressure at the moment it's easier to implement in the Eulerian. But it's quite easy to create a new part and strip it. That's not a problem. So it's under development. Okay, so that is my idea and the setup, and I applied on our engine. That is our 4-valve engine here. I will show you before. These are the operating conditions, and it is the well-known engine spray G3 that is mounted on the engine. So multi-oil injector, well validated, well known. All the simulation data are already validated, so we are not going into the details of this. This is our safety setup. So what we want to analyze is impingement rotation, mass and thickness of the film, and how it evaporates. For this, we have a full cycle runs model, which is the two model which I explained. And but this is important, the two model are different, because I want to see also if the classical evaporation model, which is actually used by default for Lagrangian spray, it's still valid for such configuration. Because actually, the evaporation model which is used now by default is a model when the particle is on the wall, it evaporates assuming that the boundary condition are the one of the cells. So let's use this occasion also to test it, this assumption. So is the buffer Eulerian concept valid? The mass evaporation must be implemented. Okay, this is what we expected in terms of because we need check methodology if it works, and we have impingement of piston, liner, and valve. So we can test everything with such configuration. It's the perfect test case. Okay, so the first one is computational cost, because we tell yes, it's important to cut it down as soon as possible. With the method, we say about 28%. Okay, that is the first achievement, at least. Why? Probably because we don't have to solve the question. Okay, so now let's compare directly the topology of the field. 15 degrees after the start. So this is the Eulerian field, this is the thickness, and this is the thickness of this is the spray. Okay, we expect the position of the projection is here, and the Lagrangian seems to be. So looking like this, okay, we reproduce the position, the dimension more or less in a cheap way, but we see that we over predict the area. And similar discussion also on the beats. Here we have the strategy, what is the prediction, and also some part where we don't expect it. But, and here is the key point. Let's look to compare the Eulerian field with the Eulerian field. Now we have exactly the same results. Oh, actually, almost comparable. Perfect. On the value, the same point on the piston, actually, almost comparable. So it seems that this approach really can reconstruct the real Eulerian field of the finite area field. Unfortunately, there is always a problem on it's optimistic because in my opinion it's just a tracking problem. Then maybe we can discuss together where is the problematic of such approach. But what is important is at least if on the piston it's working means that the concept is fine. It's just some value that must be corrected on the tracking of linear patches. So, conclusion, the buffer linear approach is valid. Some discrepancy that must be fixed for moving meshes, but fixed patches. Last, let's have a look to the power field. This is the the approach. That the classic partial evaporation fails in the near world. So the approach of evaporating the particle, assuming that the properties of the surrounding gas are the same of the cell center, actually fails for such condition. What that means that is necessary and possible, because we have now the buffer fields. It's necessary and possible also to implement the area-based evaporation source there. Still spotting this. So, in conclusion, I show you a proof of concept for a Lagrangian based wall field, which allows advanced wall field modeling and it's suitable also for topological change. A buffer, it's the trick here that it's a buffer Eulerian field is deployed to reconstruct the field properties, and specific tracking for fixed and moving patches are implemented. The morphology is reproduced, but the Lagrangian is still a bit wider. The cost of reproduced, there it's reduced. The buffer itself is valid because if we compare the Lagrangian is wide, but if you compare finite area with the Eulerian buffer, exactly the same thing, at least on that patch. Then we will fix it. Sorry. Okay. Sorry. Okay, with this I want to thank you. I want to thank our sponsor, that is the SFB project 150, and I really want to like to discuss and exchange idea with you. Thanks.
So, any questions from the audience?
Yes.
In the field, I think that is completely different because knowledge together, and so but what is the quantitative equations that you are talking to?
Yes, maybe let's return back to the algorithm. I was too fast. So yes, definitely. When the buffer polarization, of course, the configuration are different. And with the idea is that to use exactly the same equation also with this approach. The only difference is that the Lagrangian is just used to reproduce where the mass is. So for example, if you see here the white point. So for example, this is our mesh, right? So we have listen, and we have two phases. With finite approach, we say, for example, here we have a thickness, And so we have a certain mass. And here we have another thickness and another mass. And then we have evaporation tensors and with the Lagrangian field, we just say that the mass that represents this is just a set of particles which are thicker than the wall. Of course, this cannot work like this because it's not possible to reproduce all the coalescence effect and so on. So the idea is that we use this information because the mass we have, right? We have all the mass, so that's not problem. From the mass we can reconstruct a thickness field, an energy field, a velocity field. This is the so-called buffer O'Leary. So we can reconstruct all the sources. Evaporation.
All this interaction that should take into account the physics of surface tension forces to make the factor of contact of each other. And then maybe explain also why the solar regions with the field is still spectrum in the area.
Yes, for that, yes, definitely, but that is developed by the Bagel law because it's a Bagel model which says if a parcel coming from the surrounding region into the wall, which is wet or dry or depending on the velocity, the Bagel approach says us which how much mass does transfer to the wall field. So here we have our cell, we have a parcel, let's come here, impact on the wall. The Bagel approach is 1 gram, I don't know, I'm inventing, 1 gram of mass go to the wall field. Okay, no problem. For example, 1 gram of mass go to the wall field and 0.5 gram bounce back. Okay, then we bounce another parcel of 0.5 gram, and this is still the standard. So this is the Lagrangian strain. Then the parcel, it's created and stick here. So the Lagrangian is just a way to track the mass, where the mass is in our dome. Of course, to reconstruct all the stuff, we need to use a buffer O'Leary, then reconstruct as the fields, and give back the information, and then we have all the sources. When you have the evaporation model, for example, says in that finite area, if you have a thickness of 1 millimeter, I don't know, 1 millimeter, you have evaporate 1 kilogram per second of mass, just injecting, then this parcel gets reduced of 1 kilogram times the delta times. So the Lagrangian is just used to track where the mass is. And
I'm not sure if it's from now.
it's normal us to see only the first page of the presentation. No, it's not normal. Of course, yeah, the advantage of this approach is that that's the only that at the moment it's the only way that we find that it's compatible with topological change of the mesh. So let's see if the proof of concept then all fits the finite area of topological change. Let's discuss. I don't know.
Yeah.
To some extent works. Is it finite area? Yeah, because every time there is, especially in complex geometry, a lot of time it's way unstable. The topological, but we are not using that. It's funny with formation. But also to insert layering. Because here, if you see, no, not yet. The main problem that we have in the past is about the layering. So because if I remember the group of Milan and local topological change, for example, was too strong when you have the Manickam or when you use Yes. Yeah, if we don't find it, in any case, we have also 28% of computational cost. But for our case, in that case, the initialization is possible. In our case, of course, we don't have this problem because it's a direct injection spray. So we started it, we know that the spray is 0 at the beginning. So for the initialization, it's always possible to initialize a set of Lagrangian. But of course, in that case, I think that the initialization, in my opinion, it's possible. So it's just a set of parcels on the wall. That could be a possibility. Maybe why not? Yes. Yes, why not? Definitely.
Thank you very much. I'm Motohiro Oshima, in Genoa Prefecture University from Japan. So today's story is very simple story. So title is the customization of OpenFOAM Lagrangian solver for super heated pure space vaporization. Superheated vaporization flushing spray has advantages such as rapid evaporation, its contrast control of the space structure, and so on. However, the phenomena is more complicated, more complex phenomena. So this figure is the process of pressure temperature diagram. So the fuel is injected from injection pressure to the ambient pressure. So pressure reaches the vapor pressure. So evaporating starts evaporates. So as volumes are spread in the bubble, the inside droplets at the nucleus and grows and cracks. And the experimental study for superheated spray is promoted in the previous studies. However, it is difficult to simulate the evaporate by flash point spray because it considers bubble nucleation inside the droplets and heat and mass transfer. Okay, I talk about spray and combustion numerical simulation with CO2. So as you know, the keywords where we use for the energy spray numerical form, the various model is either cobalt, the source code is written in Fortran language, source code. However, it needs to software license. Unfortunately, it is not open source. As you can see, other CO2 spray and combustion, such as various CD4, OT, and so on. So, user must pay software license fee. The purpose of this study, the construction of OpenFOAM spray form for superheat spray, and we are directing this program in the future. So this is a flash boring model. So this model is proposed by Professor Richland group this model. So this figure is a strain for a pressure flow optimization model. So this model is consists of three parts. So one part is speed flash boring, a TCO model. So second part is steam evaporizing this model. And superheated rock flash boring, vaporization and heat transfer. So this is the key result. Delta T is the differences of liquid temperature, pure temperature, and boiling points. Delta T is zero. Delta T is zero is no flash boring. So straight cone angle is wider, and the force is promoted. However, unfortunately, this code is also not common. And it's atomization and combustion model. So I showed a straightforward hole connected to the Lien phenomena inside of superheated spray. So injection spray cone angle calculation is defined in the spray processing and cone injection of C. And atomization droplet size calculation is defined with atomization. The phase change, such as rush vaporization and heat transfer, is defined in the operation mode of steam. So in this study, we don't know conversion. We don't use conversion. We use off. So in this study, which radar products is customized and modified. And to show you the droplet size and spray calculation regarding to the superheat spray. This is a defined spray process C and result validation of C. So droplet size superheated combustion is calculated by using this equation. So the result is defined with equation. This model is already defined the result validation of C and the coefficients of the 7 and 0.35 and 1.88. Is defined by using straight properties. The straight cone angle is as you can see, the straight cone angle is wider in the superheated spray case. So the superheated spray cone angle calculated by using normal spray cone angle by using this equation. So heat is superheat degree parameter. Superheat degree parameter. So we compose cone angle change in straight passage of C. And next, super heat droplet flash boring and heat transfer. It is defined in the liquid evaporation boring of C. So heat transfer evaporation rate is calculated by using this equation. So here, CF is a low flash vaporization rate. So by using this equation, alpha is heat transfer coefficient. Alpha is a change by differences of liquid temperature and the boiling temperature. Here are the usage numbers in superheated spray. So changes must be changed by using step-up modification model. So, but statistical model modification model is not used because it doesn't increase the numerical result. However, flash boring cannot be calculated only customizing the source code mentioned above. So this is part of liquid operation code C code. So this task is calculation as well as the of each species in liquid part to judge flash boiling or evaporate. So you can see this curve. The droplet temperature is larger than the boiling point in superheat condition case. So this from this graph, T is equal to boiling point from this type, and the PSAT substrate pressure is calculated with the boiling point. So the flash boiling is not just the substrate pressure and the droplet of the boiling point pressure of the steam. So we change this task for basic rotating for P and PD. Let's move to the numerical condition and the computational domains. Is used isoctane. The pure temperature is 435. Superheat degrees is 60 Kelvin. So ambient pressure is 100 kilopascal. Ambient temperature is 300 Kelvin. So the total injection mass is 43.7 milligram, and most diameter is 560 micrometers. So injection duration is 3.86. For angle is defined is in figure. So alpha is 22.5 degrees, and the figure is 18 degrees. So computational domain, so total size is 5,440,000, and the injection is a center. And the diameter of the image is 200 millimeters. Okay, this is the result. The spreadsheet, the vertical cross section. Original straight form is using certain cube. So customized straight form. The straight penetration is shorter and the straight cool angle is wider. And the color is the temperature, droplet temperature. And we compare the spreadsheet feedback results. So, but the scale of the structure time is not as extreme reference. The scale factor is maybe not correct. So the spreadsheet is similar to Kiva, and the SED and straight cone angle is almost the same. And we also compare the spray penetration with Kiva. This image is the spray penetration is not the same. So reason this difference is that T-set model or not using T-set model or not. So we will include the T-set model into the spray form in the future. This is my presentation of conclusion. The flash boring numerical simulation could be calculated with the spectrum by customizing the models related to the evaporation of the superheat fuel and partial model, atomization model, of phase change model. The spray form is spray shape is similar to the Kiva, and the SAD and the spray cone is almost the same. The penetration is not the same. The reason of this difference is that using tissue model or not. This is all my presentation. Thank you very much.
Any questions for the speaker?
I didn't forget about the mental side of the body. We know state of all. That I saw that we wanted even method and what you do like this, if you specify all, you said that's the one time to all the we got it.
A boiling temperature. So, how do you calculate the boiling temperature? Is you?
No more like it's just drop temperature, right?
Yes.
And you said it in T. In T is
T is the positive temperature of numerical droplet temperature. T. Okay.
Yes, and thanks for the call. Question now, the question that the last
That's this one.
yes, maybe under the of position in the chapter with the way we can keep on the overcome. So to make the question and exactly the same way.
So spray foam penetration is at 10%. 10% of the spray appeal.
And you give on the same.
So I don't know the river, the define. So
There is exactly the same definition.
so unfortunately, I don't have the key code. So I can't compare the keeper. So the keeper has, how do you determine the penetration of the keeper? Do you know?
We can start with the definition.
I will take the new future. Second.
Because of the ball, right?
Okay, I know. So reason model is one time. So as a quick change model, like phase change model moves through also each cycle.
Right.
So different the reason model is six one time. So many times those repeated variables of C. Yes. Sorry, I can't understand your question. So Hmm. Okay, thank you very much.
Good morning, everyone. My name is Muthaiah, and I am a research scholar from the Department of Mechanical Engineering at the Indian Institute of Technology, Madras. Today, I am delighted to share with you the research and findings from the implementation of a Lagrangian model for the atomization of liquid jet in cross-flow spray in OpenFOAM. The motivation for this work comes from my focus on CFD modeling of combustion in afterburners. In an afterburner, the combustion process heavily depends on the jet-in cross-flow spray. Hence, a robust model for the atomization of the jet-in cross-flow spray is needed. Introduction of the jet-in cross-flow spray. Jet-in cross-flow spray, or JSF spray, is a widely used spray generation technique. This atomization technique is simple but also efficient. It finds usage in many aerospace applications such as gas turbine engines, afterburners, and ramjet combustors. In this method, a liquid jet is injected into a cross-flowing gas stream and is atomized by the aerodynamic forces to form the spray cloud. In the current version of OpenFOAM, there is no atomization model for this kind of spray. First, we discuss the structure of the JSF spray. The figure on the top shows the schematic of the spray. The spray can be considered to have two regimes, a jet regime and a breakup regime. The jet regime is where the injected liquid column is intact and experiences aerodynamic forces and bend in the direction of this cross flow. At the same time, small droplets are shed from the surface of the liquid column due to surface shearing process. Next is the breakup regime. After a distance, the liquid column collapses in what is known as the primary breakup process. This forms large ligaments and droplets. These large droplets further break into smaller droplets in secondary breakup process and are carried by the flow. This completes the spray formation. The fundamental mechanisms in this spray formation process are quite complex, and modeling them in a CFD framework is quite challenging. Generally, there are two approaches for spray modeling in CFD. First is the volume of fluid method, the next is the Lagrangian particle tracking method. In the volume of fluid method, both the gas and the liquid phase are resolved in the numerical grid, and this method is suitable for simulating dense spray regions, breakup processes, and droplet interactions. However, this method is computationally expensive, and when combustion is involved, this becomes even more challenging. The next is the Lagrangian particle tracking method. In this method, only the gas phase is resolved in the numerical grid. The spray is treated by considering collection of particles known as Lagrangian parcels and tracked in the numerical grid using the equations of the motion. This method is suitable for non-dense, far-field spray regions and mostly used in combustion applications. In this work, we use the Lagrangian approach to simulate the JSF spray in OpenFOAM. Introduction to the Madabushi model or JSF spray. In 2003, Madabushi developed a Lagrangian-based CFD model to simulate the atomization process of JSF spray. This model effectively predicted the spray profiles in far-field regions. Later, Madabushi et al. Improved the model based on correlations from Salam et al. For stripped droplet distribution. We implement both the models in OpenFOAM and text the experimental data from the literature. Here we summarize the Madabushi atomization model. This Lagrangian-based model has three different sub-modeling aspects. First is the modeling of injection process till the column breakup point. Next is modeling of the surface stripping process. And finally, modeling the secondary breakup process and completion of the spray. In the next slides, we will discuss each of this in brief. In modeling the injection process, instead of a cylindrical jet, spherical particles with the same diameter are injected. However, the coefficient of the drag is adjusted to that of a cylinder to have a correct aerodynamic behavior. The particles are tracked and considered to be inside the liquid column till the column breakup point. The time period of the column breakup is calculated using the correlations given by Wu et al. As shown here. When the parcels are inside the liquid column, surface stripping of the droplets occurs, And this surface stripping is modeled using the wave model based on Kelvin-Helmholtz instability. The expression given here is used to calculate the rate of reduction in the parent parcel diameter. Here, d is the diameter of the parent parcel and dc is the stable diameter after Kelvin-Helmholtz breakup given by the wave model. And tau is the time period of the breakup process estimated using the wave model. Using this expression, the diameter and the mass of the parent parcel are continuously reduced and the stripped mass is accounted separately. The reduced diameter from the parent parcel are continuously accounted as stripped mass. When the stripped mass is greater than 5% of the parent parcel, a new child parcel is added with the mass of the stripped mass. The diameters of the child particles are assigned in two ways. One is using the stable diameter dc estimated using the wave model. This is considered in the variant 1 of current implementation. The next is the child diameter are estimated using correlations given by Salam et al. And this is used in the variant 2 of the current implementation. Later, then, the velocities of the stripped parcels are assigned as a combination of the injection velocity and the gas phase velocity as given here. Next is modeling of the secondary breakup process. Parcels coming out of the liquid core are broken up in this process. Each of the spherical particles coming out of the liquid core are broken into 5 child parcels based on local Weber and Onnesage numbers. The time period for each of the 5 breakup events are estimated using the expression based on gas phase velocities, gas phase Weber numbers as given here. A child parcel is added at each of these breakup times and the child parcel SMD is calculated using the expression given in this box. Large parcels resulting from this secondary breakup process are again subjected to the wave model that is mentioned previously. With the Madabushi-Lagrangian model is introduced and summarized, we state the objectives of the work. The objectives are to implement both the variants of the Madabushi atomization model in OpenFOAM, validate these models with the data from the literature, and identify potential improvements to the models. Here we list the implementation and the modification work that we carried out. Before moving on to the implementation, we looked into the existing models, and the major issue in the existing atomization part was there was no coupling with the gas phase during the atomization part. That is, the liquid droplets that are injected don't feel any aerodynamic forces, and there was no surface stripping model, and it needed a new class of model to be implemented in the Lagrangian library. Here are the modifications that are carried out. We implemented a new atomization model with gas phase coupling. We implemented a new class of breakup model for simulating surface stripping, and it was based on the existing Wright KHRT breakup model. And we also implemented a secondary breakup model based on the work of Madabushi et al. Here are the results from our implementation. The figure on the left shows the liquid core and the surface stripping process, where we can see the liquid core in red and the small droplets are shed from this liquid core. The figure on the right shows secondary breakup process out of the liquid core. We implemented the two variants of Madabushi model by modifying the existing spray foam solver. Then we move on to validate the implementations using data from the literature. We chose data by Wu et al. And Lien and Hartmann. We ran multiple test runs using compressible and steady RANS calculation with the K omega SST turbulence models. The computations had a similar setup in which there is a flow in the duct simulating the cross flow into which the spray is injected perpendicularly as shown in figure. In the coming sections, we show results from each of the validation cases. This is the test case 1, and this configuration is based on Wu et al. The computational domain is given in the figure. It is spray from our implementation. And the boundary conditions are given in the table. The spray liquid used in this calculation is water. Here the water is injected with a velocity of 29 meters per second into a cross flow stream of 103 meters per second. Here are the results from test case 1. The data is extracted 150 mm downstream of the injection plane, that is in the far field. The figure on the left shows the velocity comparison, stream-wise velocity comparison, and the figure on the right shows the SMD comparison. The x-axis here is the transverse distance into the cross stream, normalized by the injected diameter of 0.5 mm. The blue dots here represent the experimental data, and the black line is the data from the Madabushi's work. The green line is the variant 1 of the current implementation, and the red line is the variant 2 of the current implementation. The data sampling plane is given in the inset of the left figure. Looking at the left figure, we can see that the velocities are predicted reasonably well by both the models, including the trend. However, the model 2, noted here with the red circle, has a better prediction in the lower part of the frame. Above the height of y by d 40, even the Madabushi's data shows a large deviation, but the model 2 has a good agreement. In the secondary breakup part, that is in the top part of the plot, both the variants 1 and 2 have same prediction close to the experimental data. Looking at the SMD plot on the right, we can see that the trend is predicted reasonably well, but the lower part is in the lower part, the model 1 overpredicts the SMD. However, the model 2 has a better prediction. In overall, model 2 has a better prediction in the far field. Next, we tested against the data from Lien and Hartmann for near field character. The flow configuration is shown in the table. The spray liquid used here is Jet A, and the Jet A liquid is injected with the velocity of 31 meters per second into the cross flow stream of 148 meters per second. The injected diameter used here is 1.778 mm. Here are the results from the validation study 2. The data is extracted 1 inch downstream of the injection plane, that is in the near field. Again, the left figure is the velocity comparison and the right is the SMD comparison. The blue dots are again the experimental data from Long and Hartmann, and the black line is the reported data by Madabushi. The green is the variant 1 of the current implementation, and the blue lines, red lines are representing the variant 2 of the current implementation. Looking at the velocity plots, large deviations with the experimental data could be observed. However, the trend is predicted better in the lower part by the variant 2 of the current implementation, that is the red line, and in the upper part, the variant 1 predicts close to the experimental data. Notably, the trend is predicted better than the reported data by Madabushi himself. Looking in the plot on the left, right, that is the SMD plot, you can see the model 2 predict very close to the external data in the lower half of the spray. Going further into the cross stream, the model start to over predict above a distance of 15 mm and continuously over predicts. And the model 1 is consistently under predicting the experimental data, but it is has a similar trend to that of the reported data by Madabushi. This completes our validation study. Here are the conclusions from our study. We implemented and validated both the variants of Madabushi model in OpenFOAM. The results are generally in agreement with the reported data and encouraging. Both the implemented models, version 1 and 2, correctly predict the trend. However, the model 2 with the correlation by Salam et al. Tend to overpredict the near field SMD of the surface stripped parcel, but gives improved prediction at far field condition. This is seen in the validation study 1. We believe that using the Salam et al. Correlations only in the far field region can help in improving the predictions by these models. These are the references used. Thank you.